Because I've been forgetting the past few days and nobody called me out or nothing. I'm like, all right, I'll be forgetting to record. Now I recorded it, but it's like I start reading and I'll be like, oh, let me take it back. Let me do it again. All right, so that's what we're getting into today, right? Sample size for estimating the mean, mu. All right. You remember doing this? Yeah. Okay, okay. So, all right. So, in the design stages of statistical research projects, it is a good idea to decide in advance on the confidence level you wish to use and to select the maximal margin of error, E, right? You want for your project. How you choose to make these decisions depends on the requirements of the project and the practical nature of the problem. Whatever specifications you make, the next step is to determine the sample size. All right. So solving the formula that gives the maximal margin of error E for n, our sample size, enables us to determine the minimal sample size. All right. Blah, blah, blah. This is how you do it step by step. This is the procedure, right? So, how to find the sample size n for estimating mu, your population mean, excuse me, when you know what sigma, your population standard deviation is, right? When sigma is known. So, requirements: the distribution of the sample means x bar is approximately normal, right? Here's the formula right here. The formula for the sample size is n is equal to open parentheses z critical times the standard deviation divided by your margin of error, close parentheses squared. All right. Just to recap, right? So E is your specified maximal margin of error. Sigma is your population standard deviation. Z critical is your critical value from the normal distribution for the desired confidence level, C, right? Commonly used values of Z critical can be found in the table, right? We know that already, or of the appendix.
Or
Mhm.
it's a little more difficult. Before
Yeah.
when to find T,
Oh, we didn't even get there yet. That's tomorrow.
yeah, that's
Yeah.
another topic.
Yeah, that's another week. Yeah. Yeah. All right. So if n is not a whole number, increase n to the next highest higher whole number. Note that n is the minimal sample size for a specified confidence level and maximal error of estimate E. All right. Let me just make a comment. So if you have a preliminary study involving a sample size of 30 or larger, then for most practical purposes, it is safe to approximate sigma with the sample standard deviation S in the formula for the sample size. All right. Let's do an example real quick. All right, so this is an example. So a wildlife study is designed to find the mean weight of salmon caught by an Alaskan fishing company. This sounds good. A preliminary study of a random sample of 50 salmon, that sounds expensive, showed that there was a sample standard deviation of 2.15 pounds. How large of a sample would be taken? Oh, no, excuse me. Let me say that again. How large a sample should be taken to be 99% confident that the sample mean X bar is within 0.2 pounds of the true mean weight of mu? Let's take a look at what we have real quick. Hold on. Let me get this. So we have a sample standard deviation of 2.15 pounds. We have a random sample of 50, right? We want to be 99% confident, right? And we want X bar to be within 0.20 pounds of the true mean weight, right? Let's write down what we have real quick. So my random sample N is 50, right? My sample standard deviation S is 2.15, and my confidence level is 99% or 0.99. Yeah, I put capital C and capital L for my name. I know. I'm that important. All right. And then we want our sample mean to be within 0.2 pounds of the true mean. So really and truly, what I'm trying to tell you is that My maximum margin of error that I want is 0.20, right?
What if TCL here in this case? The
The confidence level.
the confidence level.
Yeah. Because it's my initials, that's why I do that, like it's like I feel important. Yeah. So next, I want to do the formula, right? So let me go to the formula sheet so I could copy the formula. S is sample standard deviation. Huh? Not the average weight, but the spread of the data of all the fish that you caught. So I'm on why is this here? 1 second. I'm on my formula sheet, right? So I have to copy down the formula for this problem. Even though I just said it, I forgot what the formula was. No cap. All right. So here's my formula, right? Sample size for estimation, right? So N is equal to chapter 8, yep. N is equal to Z critical times sigma divided by your margin of error squared. So there we go. You can't see? Okay, okay. Oh my God, that is so far. Hey, how you doing? You want to eat?
Está bem, graças.
That thing is mad far. All right. Anyway. Awesome. All right. So all I got to do is just plug this in. I just have one problem. I need my Z critical, right? More specifically, I'm looking for Z 0.99. Yeah. So let's look up the 0.99. Let's use a table. So I just go to my formula sheet, right? And I want to turn to where the normal distribution is. Blah, blah, blah. Okay. So now we have our areas of a standard normal distribution. 2.5a. Okay, that's probably what it is. Yeah. So what I'm doing, I'm just scrolling down to the bottom right here where it says confidence intervals, right? And I want 99, right? So here goes 99. And there's a Z critical, 2.58. And that's it. All right. Coming back here. So this is 2.58. All right. After all of that, just plug it in the formula. You're done with the whole question. Look at this. What's Z critical? 2.58 times what's the standard deviation? Hold on. What's the standard deviation? 2.15. Yeah. Over my margin of error E, which is what? 0.2 squared, right? Just to be clear, the reason why I can use the 2.15 here is because my N is 50, right? Z interval? Z critical. Yeah. Remember when we have the distribution like this and 99% of the data is in the middle? Right, and you want to find Z critical right here? That's what that is. The other side is negative Z. Hmm. Mhm. That's your Z critical, right? You got that straight from the formula sheet.
Because I care every day, but I'm paying attention right now, right? But I know, this very.
No lie, like when I touched this, it became wine.
Yeah, like. Okay. Sorry. All right. That's not. No.
It's all good. It's all good. So look on the formula sheet, right? Hey, what's good, man? How you doing? Yeah, I saw you coming to campus, man. Got you. Yeah, you did your pantry yesterday. Yo, you hungry? You hungry? Yeah, man. Yeah. All right. Yeah, you're welcome. All right, so on the formula sheet, right, at table 3, the confidence level was 0.99 or 99%. So our critical value is 2.58. And that's it. That's where it came from. So after that, we just put it all together. And that's the end of it, right? Stored in the calculator, and that's it. Mhm. Yeah, they're gonna tell you specifically like I want the confidence interval or I want the sample size. Like they're gonna ask you for it. They're gonna ask you for the confidence interval. Z critical? Yeah. Those are a few of them, right? If it was like say you're looking up a question that's in like another textbook or something, right? They might give you a confidence level that's not on that sheet. Say like 98%, which is not there, right? 98, yeah. 98 is there? Okay, like 65, right? So but you know how to find that, right? It's this way. Uh-huh.
Can you just go over the only thing I'm trying to understand is when you get to the critical, no, wait, you think I'm right, so? What is it called?
Right? And then you know that you just cut these in half, right? So what is that, like 35? What's half of 35? 17, 17.5. All right, so you got 17.5 here, and you got 17.5 here. You just look it up in the table. Right? Remember when we look in the normal distribution table to find it? So that's how you would do it if it was not on that little table on the bottom. Hmm. But in real life, you might encounter things like that, you know? Yeah. Uh-huh.
This is T. That's a C.
C, yeah.
That means what's the product?
No, that's technically speaking, that C shouldn't even be there. Technically speaking, that should be 0.65. Yeah, that's Z critical. And in between it is a multiplication sign. Yeah, like that. So it's the number of standard deviations, right? Like away from the mean a number is.
Oh, so that's the number. The number next to it is it.
Yes. Yeah. All right. What? Why? No lie. Look, when you see a question and they say, "All right, give me the sample mean," right? I'm just give me the sample size, right? You whip out this formula, you plug in the numbers, and that's the end of the question. That's it. It's literally that simple. Oh yeah, you have to do the math. Yeah. Web work. You know how web work be? Yeah. Does everybody know how to do this in their calculator? Or do y'all need to see it done? Why? So go to the tutoring lab and borrow one. The tutoring lab and the library are not the same people. Hmm? No, you can't. You need the confidence level. Yeah. Yeah. Yeah, and that's it. Light work. So the question gave me a confidence level of 99%, right? And then I just went to the table, right? When I was on the table, I went down to where 99% was, which is down here, right? And then I just copied the ZC, which is right next to it, which is 2.58. That's it. That was given in the question. That was given in the question. That's that last sentence. You see where it says X bar is within 0.20 pounds of the true mean? Margin of error. Yeah. Whatever the question tells you it is, that's what it is. Yeah. Yeah. But what do you care though? Just type it in a calculator, click enter. Yeah. Mhm. Nah, this is yeah, nah. What is that? Oh, it's a spider? Yo, step on that shit, man. Man. Yo, I thought that was a fly. I didn't think it was a spider. Yeah. Yeah. Damn.
You just killed it. No.
Yeah. It does, you're right. Yeah.
So you're messing up the.
Word. Yo, imagine he turning to Miles Davis. All right, real quick, y'all good or y'all need to see this in the calculator? Another what? Oh yeah, I got more problems for you.
Or, how we find value is.
They just give it to us. Yeah, just give it to you. Yeah. Yeah. Nah, but it tells you. Nah, it tells you flat out what it is. Yeah. Nah, it should be there. Hold on. Damn. My fault. Y'all know I got mad pop-ups every time I be opening my calculator. Yeah. I don't have an app. I just have the website. Yeah. But I want y'all to see what the official calculator does, that kind of thing. You could, but I don't want round off error, so I just plug everything in. What? Really? Yeah, all you got to do is just plug it in the same way it looks, you know? So watch, like if you're on the 36X Pro, just press that fraction button right above number 7. First, you got to open parentheses though. All right. And then press the fraction button. For us, that's going to be alpha F1. If you got a 36X Pro, you know that's the button right above the number 7. Literally, just type it in the same way you see it here, right? 2.58 times 2.15. Then go down 0.2. Then go across, you get out of it, close parentheses, and then square it. And that's it. Boom. Oh Lord. 7, 6, 9. Hey, 6, 7. All right. 0.230225. All right. Now, this is key. I'm talking about a sample size, right? What the hell is 0.230225? What the hell does that even mean? Right? Whenever you're doing a sample size, always round to the next whole number, right? So my final answer is going to be 770. All right. This is whenever I'm sorry? Whatever decimal is here, right? Whenever you do this, right? You're looking for a sample size, go to the next integer, right? The next whole number integer. So instead of 769, 770, right? Because 0.230225, that don't make sense, right? So when I run my experiment, I know that I need 770 individuals to do my normal distribution, etc. On the calculator? All right, for you, it's a little bit different. Uh-huh. Always up, always up, always up. Yeah. Always up. Yeah. Yeah. Always up. So if it was like 769.0123, going to 770, right? So decimals make no sense, always up. After say that? 755. Yeah, yeah. All right, so Carmen, for you, right? Open parentheses, all right? And then you want to do 2.58 times 2.15 divide 0.2 close parentheses, right? Then you want to raise it, touch the little caret here to the second power, then enter. It's not going to look like mine, but that is the actual process. The caret right above the division sign. Mhm. And then 2, and then hit enter. Yeah. Mhm.
The word,
Yeah. Yeah.
Yvonne, actually,
Mhm.
Yvonne actually did a word.
Yeah.
Mr. Lee, so you sure I can take a look of the album? Okay.
Yeah.
Cause one time.
Just give it back after the test. It's easy. You take it out before the test, and then you give it back after the test.
Like, 3 weeks.
No, no.
That's,
Yeah. I'm sorry? Not like this, but yeah, there's other examples. Yeah. It worked, right? Yeah. It worked? Good, good, good. All right, let's get back to it. Go across, listen to me. Okay. No Jovine? Oh shit. About to take advantage now. Mhm.
That means we are on the clock.
Nope.
Oh.
I'm taking advantage. Nope. I'm taking advantage. Y'all already got this homework, so might as well.
The same thing that we just talked about yesterday.
Yeah, but we taking it up a notch right now. All right. Yep. New topic. So look, estimating mu when sigma is unknown. Oh shit. It's the remix. All right. So in order to use the normal distribution to find the confidence intervals for a population mean mu, we need to know the value of sigma, right? The population standard deviation. However, much of the time, fuck it, let's keep it real. All of the time, right? When sigma is unknown, right? Or excuse me, when mu is unknown, sigma is unknown as well. In such cases, we use the sample standard deviation S to approximate sigma, right? When we use S to approximate sigma, the sampling distribution for the X bar follows a new distribution called a student's T distribution. All right. So let's talk about a student's T distribution. So students' T distribution were discovered in 1908 by W.S. Gossett, right? First name William, but I don't know. So he was employed as a statistician by Guinness Brewing Company. Yes, that's the same Guinness that we all drink, right? A company. Oh, y'all don't drink Guinness? Oh, yeah, I forgot y'all young, y'all young. My fault, my fault, my fault, my fault. Wait. When y'all grow up, yeah, my fault, my fault. Right? So the Guinness Brewers Company, a company that discouraged publication of research by its employees, as a result, Gossett published his research under the pseudonym Student. So Gossett was the first to recognize the importance of developing statistical methods for obtaining reliable information from samples of populations with unknown standard deviations, population standard deviations. So Gossett used the variable T when he introduced the distribution in 1908. To this day, and in his honor, it is still called a student's T distribution. It might be more fitting to call the distribution a Gossett's T distribution. However, in the literature of mathematical statistics, it's known as a student's T distribution. The variable T is defined as follows. A student's T distribution depends on the sample size N, right? And, woo, missed the good part. Let me get the rest. Let me get the rest. Taking advantage. Taking advantage.
Right, there you go, you spoke too much.
Taking advantage.
Yeah.
So assume that X has a normal distribution with mean mu for sample size N, with a sample mean, right, X bar, and a sample standard deviation S, the T variable. So here is your formula for a student's T distribution. Is T is equal to X bar minus mu over a sample standard deviation over the square root of N, right? And it has a student's T distribution with, this is new, with a degrees of freedom equal to N minus 1. You need this to look up the distribution. All right. Those of you that take notes, this is the part that you write down. All right. The blue box.
Yeah.
Yeah. Oh, nah. Nah, these birds, they be smashing on campus. You know how that be. Hmm? Yeah. I'm pretty sure Flacco came to BCC when he was free in Manhattan a couple of times, you know. You know, the Bronx community birds ain't the same as the Manhattan birds. Our pigeons are different. Yeah.
People and.
All right. If many random samples of size n are drawn, then we get many t values from the equation, right? These t values can be organized into a frequency table and a histogram can be drawn, thereby giving us an idea of the shape of the t distribution for a given n. Fortunately, all this work is not necessary because mathematical theorems can be used to obtain a formula for the t distribution. However, it is important to observe that these theorems say that the shape of the t distribution depends only on n, provided the basic variable x has a normal distribution. So when we use a t distribution, we assume that the x distribution is normal. That's important. All right. Table 4 of our appendix, which I'm going to go to in a minute, gives values of the variable t corresponding, to what we call the number of degrees of freedom, abbreviated as df. All right. For the methods used in this section, the number of degrees of freedom is given by the formula df is equal to n minus 1, right? Where df stands for the degrees of freedom and n is your sample size. Each choice for the degrees of freedom gives a different t distribution. The graph of a t distribution is always symmetric about the mean, which as for the z distribution is 0. The main observable difference between a t distribution and a standard normal z distribution is that the t distribution has somewhat thicker tails, right? So the next figure is going to show you that a standard normal z distribution and a student t distribution with the degrees of freedom of 3 and degrees of freedom of 5. So let me get that for y'all. This is exciting. Oh, shoot. Here we go. It looks like the Z formula, right? No, it's the same as the Z formula. Huh? The formula? Yeah. This one?
Yeah.
Is that all connected?
Yeah.
The S is there's two.
Just put a parentheses around it and you'll be good to go. Yeah. But we'll get to that though. We're not gonna get to that till like chapter 9. Yeah. But I want y'all to see it right now though. So check this out. Check this out. So this is a standard normal distribution and a student t distribution with degrees of freedom 3 and degrees of freedom 5. All right. So the normal distribution, that's the red line or the pink line, whatever it looks like on the screen, right? Now the black line, right? That's degrees of freedom 3, and the blue line is degrees of freedom 5. What I want you guys to notice though, right? When you look at the normal distribution, look at these tails. You see how the tail is like right there on top of the x-axis, right? But for the other ones, for the t distributions, you see how they're approaching the x-axis, but they ain't reached there yet, kind of thing. So their tails are thicker. That's what they mean by thicker. Like it is gonna go to the x-axis. It just says that in a t distribution, it takes longer to get to the x-axis compared to the normal distribution. Right? Will it ever touch the x-axis? No, but it's gonna get close and closer and closer. Go ahead. It's the tails right here. This is the difference, right? The normal distribution is really, really close to the x-axis right here. That's the pink line, right? So, but for students t distribution, that's the blue and the black line. It takes longer for them to get to the x-axis. That's the only difference in the graph. All right. Right. There's a degrees of freedom for the black line of 3 and a degrees of freedom of 5 for the blue line. I'm gonna show you like where that comes from and all that, or why we do that. I haven't gotten there yet.
He's not quiet.
What?
He finished his homework already, so he knows all this. Yeah.
Please continue.
Yeah.
That's crazy.
So properties of a student T distribution. The distribution is symmetric about the mean zero. The distribution depends on the degrees of freedom, right? So DF, and the formula for DF is n minus one for population mean mu confidence interval. The distribution is bell-shaped, but has thicker tails than the standard normal distribution. As the degrees of freedom increases, the T distribution approaches the standard normal distribution, and the area under the entire curve is 1.
It's really saying grass, because
Mhm.
this,
Yeah, yeah.
I'm understanding drawing.
I'm happy you enjoy understanding drawing. Mhm. No lie, my alarm in the morning is birds chirping, so like now I feel more awake. Yeah. Yeah. It took a long time for me to get used to the birds chirping though. So I have this app, right? And in the app, like it has a silent alarm to like kind of wake you up like a couple minutes before your real alarm. So my real alarm is like a radio with like mad nice music, right? And it just like blasts from my phone. But before it gets there, it has like a little birds chirping. Like it's a little bit, then it gets a little bit louder, a little bit louder, a little bit louder. Yeah. Thanks. Thank you. Thanks. Yeah. But you know what the problem with my alarm is though? When it goes off, for me to snooze it, I gotta do math problems. Yo, so that shit is like torture. I'll be like, yo, what's 2 times 3? Like I know this shit. Cause I'll be halfway asleep. So I'm like, God damn. And I can't even Google it because it locks the phone. Like you you can't swipe up to go past it. So it's like I gotta know, like, yo, 2 times 3. Like yo. Yeah. Yeah, but it works. It works. All right, so using table 4 to find critical values for the confidence interval. Table 4 of the appendix gives us various t values for different degrees of freedom, df. We will use this table to find the critical values, t critical, for the C confidence level. In other words, we want to find the t critical such that the area is equal to our confidence level under the T distribution for a given number of degrees of freedom that falls between negative T critical and positive T critical. In the language of probability, we want to find the T critical such that the probability of negative T critical is less than T, which is less than T critical, which is equal to the critical level, right? This probability corresponds to the shaded region in this graph. Let me show y'all. Yes, I'm showing y'all the same graph that y'all been looking at all day. Here it is. Nickelodeon. Oh, she do? Okay, I got y'all. Y'all want y'all break at the end or y'all want y'all break it in right now?
Say that again,
Yeah. I'm almost done though. I'm almost done. Just one example and I'm done. Yeah. So look, figure 8.6, which is this, right? The area under the T curve, which is between negative T critical and positive T critical. It's the same thing that y'all just saw with the Z, but now it's T, right? Different mathematical formula, right? If anybody wants to switch to calculus in the future, then we could look at this again and I could explain a little bit more. Mhm. Yeah. I know Danny's switching to calculus, right? Oh, dang. Yeah. Yeah. Calculus is way easier than this anyway, so yeah. Yeah, way easier. This is more work. Statistics is built off of calculus. Hey, what's good, man? Right. So table 4 of the appendix has been arranged so that the critical level is one of the column headings, and the degrees of freedom DF are the row headings. So to find T critical for a specific critical level, we find the column headed by the critical value and read down until we reach the row headed by the appropriate number of degrees of freedom. Right. So you will notice 2 other column headings, one tail area, 2 tail area. We'll use those later, but for the time being, just ignore them, right? So let me take y'all to the formula sheet so y'all can take a look at what I'm talking about. So I take out my formula sheet, right? This is what I'm talking about. You see this table right here? This is the last one, the last sheet on your formula sheet, table 4, right? You see where it says DF? Right here, you see the DF right here? These are your degrees of freedom going straight down. Right? Say it again?
Yes, it's a,
3 and 5? Oh, yeah. So then, like, this is degrees of freedom 3, and this is degrees of freedom 5, right? Right? Look at right here. You see where this C is? This is your confidence level. And here are all your different confidence levels for T distribution right up top here in this row. All you're doing is matching them. Where do they intersect that? And then these individual numbers here, those are your T criticals. That's it. All right, nice and simple. All right, let's gives you the T critical, which is what these numbers over here. All right. So let's get into it real quick, right? So convention for using a student's T distribution table. If the degrees of freedom DF you need are not on the table, use the closest degree of freedom in the table that is smaller. All right. This procedure results in a critical value T critical that is more conservative in the sense that it is larger. The resulting confidence interval will be larger and have a probability that is slightly higher than your confidence level. All right. Let's take a look at an example. This about to be fire. So here's our first example, right? So we want to use this table, right? A3, right? An excerpt from table 4 of the appendix to find the critical value, T critical, for a 99% confidence level, right? So 99% confidence level for a T distribution with sample size n equals 5. All right, huh? All right, we're gonna take a look. Real quick, if my n is 5, then my degrees of freedom is equal to, not 5, my degrees of freedom is equal to, right? No. So degrees of freedom is n minus 1, right? So if my degrees of freedom, excuse me, is 4, right? So it's gonna be 5 minus 1, which is equal to 4. That's it. Now we can look it up in the table, all right? I don't know.
It will be 4.604.
4.604?
Yeah.
All right. Let's take a look.
Let me see the straight. I've got n minus 1.
So my degrees of freedom is 4,
Yeah. Then
and my confidence level was what, 99? Right? So I go up here, I find 99. Go down, so 4.604. That's it. All right. Mhm. And that's it. Questions about this?
That's the easy part.
That's the easy part?
Hold
All right.
on myself.
All right, go ahead. So your degrees of freedom is 4, right? So you go down 4, and where the C is, go across to 0.99. And then what number do they intersect at? Yeah. Yeah.
You got.
All right.
And this one is T what?
T critical. Yeah. You got it? Z critical, yeah. Mm-hmm. Yeah. Good. All right, and I can hear Danny's question, right? So how do we do this on the calculator, right? Here we go. Y'all know Danny always want to know that.
No.
Yeah. He was yawning, but I know that meant like, yo, let me see it on the calculator. I got you. All right. All right, this is going to be really, really special. Not everybody is going to be able to do this. All right. I don't think you could do this on your calculator, Carmen, but I want you to try. All right. So, yeah, I want you to try. Let's see. So you're going to go to second distribution. All right. I forgot I need this information right here. You're going to go to second distribution. Then you're going to go to where it says inverse T, number 4. I don't know if you see that, but INVT. INVT. Like look at what mine says. INVT. Do you see that?
Yeah.
Number 3? Okay, cool. So you're gonna click it, right? They're asking you for your area, right? What area am I gonna put in? That, huh? 5? No. The area is the no inverse T. INVT, capital T. So what area am I putting in? Yes, the confidence level, yeah. No. Huh? If you could do what? Yeah, you probably could inverse T. So look. Here's what I'm gonna show y'all. Yeah, you might not have it. That's why.
Nah, we get that one here.
Yeah, that one got it. The 84 got it. 84 got it.
That
Second distribution. Yeah. And then go to INVT.
Oh, yeah.
Yeah.
Enter?
Yeah. Hit enter.
Okay, good.
Yeah. So look, you remember this graph right here? I need y'all to think about that graph real quick. All right. Yes, my confidence level is 0.99. But remember, when you draw it out, 0.99 is right here. And I want T critical. But what's this? Mm-hmm. And then this is 0.05. So in the calculator, I have to put this area here in there, right? So that's 0.995, right? So 0, oh shit, I messed it up. You don't need it. You got the table. What's the degrees of freedom? Degrees of no, it's right there. What's degrees of freedom? Four. Right. And then you just paste it. Bam. Oh shit. Hold on. Boom. 4.604. There it is. All right. So that's how you do it in the calculator. Yeah, I agree. Not everybody has this, right? This is like on the 84 color edition, whatever, you know? But that's for you, Danny. Hmm. And if y'all want to review it, y'all could just look it up in the video. Mhm.
How many before that exam people posted the topic that you made the exam?
I do.
How many days before?
Couple days, not many. Couple days, because I have to finish teaching before I could do that. You know. All right. That was fun, right? For real? All right, let's take it up a notch. Same thing like what we did before, right? Because y'all know I'm only doing this so that I could do what? Find a confidence interval. Let's talk about that. So here you go. Confidence intervals for mu when sigma is unknown. So in the last section, we found plus or minus E on the margin of error for the C confidence levels. Using the same basic approach, we arrive at the conclusion that our new margin of error, whenever sigma is not known, is unknown, right? Is T critical times your sample standard deviation divided by the square root of n. Right, this is the maximal margin of error for a confidence level when sigma is unknown, right? I.e., the absolute value of x bar minus mu is less than E with a probability of our confidence level. The analog of equation 1 in the first section is this is going to be the probability of negative T critical times the sample standard deviation over the square root of n, which is less than x bar minus mu, which is less than T critical times sample standard deviation over the square root of n, which is equal to the confidence level. Yippee. All right. Here's a comment comparing equations 14 to equation 1 in the first section. It becomes evident that we are using the same basic method on the T distribution that we use on the Z distribution. Likewise, for samples from normal populations with unknown sigma, right? We use the same formula, x bar minus E less than mu less than x bar plus E. That we want the probability of that, which is equal to our confidence level, right? Where our margin error E is now T critical times the sample standard deviation over the square root of n. Let us organize what we've been doing into a convenient summary. All right. Literally, we're just doing the same thing we did last section. All right. This next part is for Sarah, though. Yeah, this for you.
You, Sarah.
You want, I know Sarah always wants that step-by-step procedure, how we do this. I got you. Here it is. All right. So how to find a confidence interval for mu when sigma is unknown. Requirements. Let X be a random variable appropriate to your application. Obtain a simple random sample of size n of X values from which you compute the sample mean X bar and the sample standard deviation S. If you can assume that X has a normal distribution or simply a mound-shaped symmetric distribution, then any sample size will work. If you cannot assume this, then use a sample size for n greater than or equal to 30. Remember this formula? It's the answer to everything right here, right? So x bar minus E less than mu less than x bar plus E. That's our answer for a confidence interval. Where x bar is our sample mean of a simple random sample, Our margin of error is now T critical times the sample standard deviation over the square root of N. Our confidence level, once again, is between 0 and 1 because remember, it is a probability. And our T critical is our critical value for confidence level C and a degrees of freedom N minus 1. Yippee. All right. One last comment, then we're going to go into an example. No lie, we might get out of here early today. Yeah. Isn't it 5:36? Yeah. We might get out here early. You'll understand it, don't worry. In our applications of students' t distribution, we have made the basic assumption that X has a normal distribution. However, the same methods apply even if X is only approximately normal. In fact, the main requirement for using a student's t distribution is that the distribution of the X values be reasonably symmetric in mound shape. If this is the case, then the methods we employed with the t distribution can be considered valid for most practical applications. For example, y'all ready? Last example. Last example. Let me check something. All right, we good. It's got a little bit of a summary after this, and then we out.
Why
Alright.
you are rushed?
Hmm?
Why you are rushed?
I'm chilling.
Oh, okay.
I'm chilling, yeah. So confidence interval for mu when sigma is unknown, right? Suppose an archaeologist, this is an example, right? Suppose an archaeologist discovers seven fossil skeletons from a previously unknown species of miniature horse. Cool. Reconstructions of the skeleton of these seven miniature horses show that the shoulder height in centimeters to be 45.3, 47.1. You can read the rest, whatever, right? For these sample data, the mean is X bar is equal to 46.14, and the sample standard deviation is S is equal to 1.19. Let me highlight those because those sound important. All right, X bar 46.14, sample mean 1.119. Let mu be the mean shoulder height in centimeters for the entire species of miniature horse, and assume that the population of shoulder heights is approximately normal. Find a 99% confidence interval for mu, the mean shoulder height of the entire population. Cool, cool, cool. All right, let's just recap. Let's write down what we have. We don't have a lot. All right, I have X bar, which is 46.14. You guys know how to find that, right? Just add them all up, divide by how many numbers are there. That's how you find that, right? Same thing, right? Our sample standard deviation is equal to 1.19. Y'all know how to find that, right? That's just right back in chapter 3. Remember that standard deviation formula? Bop, 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 you get the answer, right? Our confidence level is 99% or 0.99. All right? Let me ask you guys a really hard question. What's my sample size? What's N? How'd you get that? How you got 7? Counted. That's what I'm talking about.
Oh, you're funny.
That's what I'm talking about. Right? Because I was real mean. I should have really done this. Oh shit.
Yeah.
I should have done this, right? I should have highlighted it. No, 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 no. That was the right procedure, right? Yeah, yeah. So now, right? What's my degrees of freedom?
Have to stop, right?
Mhm.
Oh.
What's the
six.
formula?
Six.
It is 6, right? So N minus 1, which equals to 7 minus 1, which is 6, right? All right. So now we have our margin of error formula. E is equal to T critical times the sample standard deviation over the square root of N. You might be wondering if I'm making all of this up. I'm not. It's on the formula sheet, right? Let me show y'all. So I turn to my formula sheet, right? I just got to turn to the first page, then just turn it right over to the next page in chapter 8. Here we go. This is my E formula, my margin error formula right here. T critical times sample standard deviation over the square root of N. When sigma is unknown, I don't know what sigma is. I know what the sample standard deviation is. With the degrees of freedom of N minus 1. So if you ever forget, it's on the formula sheet. Just copy. That's it. All right. Let's go back to the question. And this is mad simple, right? All we got to do is just plug in the numbers. We already know what the sample standard deviation is. That's the 1.19 over the square root of N. We already know what that is. That's 7, right? Times our T critical. What's my T critical? Oh, shoot. Let's look that up. So I have a degrees of freedom of 6, confidence level 0.99. I got to go to the formula sheet. What you got? Yeah, I got you. I got you. I'm going back to it. I'm looking up the value right now. T critical, T. Right. So we use Z critical when we know what the population standard deviation is, but we use T critical when we only know the sample standard deviation, S, on the student T distribution table. Right. So my degrees of freedom, we said, was 6, right? So here goes the 6 right here. 99, right? So go across to 0.99. And then where do they intersect at? Huh? 3707. Yep. That's it. Yeah. So you go to the 6, that's your degrees of freedom, and your confidence level is 0.99. Boom. Right? So 3.707. All right? Uh-huh. Yeah, 6. Hold on one second. How do I cancel this? You go to 6 for your degrees of freedom, and then at the top you have your 99, 0.99. And you just look at where they intersect that, which is the 3.707. 3.707. All right. After that, just write it down. Right. So that's the 3.707. Just write that in, 3.707. All right, after that, little calculator, boom, 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 and we're good. All right. I'm gonna do this right here because I just showed y'all how to do this in the calculator. I know y'all all know how to do it. So we good. All right, so this is 1.19 times the 3.707 divided by, right, the square root of 7, right? Bam, bam. And here we go. Here's my number. I got 1.667326. Easy. Easy, right? So look at this. Here goes the answer. Straight from the formula sheet. X bar minus E less than mu less than X bar plus E. Just plug them in, right? What's X bar? The 46.14. Plug it in. 46.14 minus the E, the 1.667326, less than mu, less than the formula sheet, chapter 8. Yeah. 46.14 plus the 1.667326. A little bit of math, and we good to go. Right? So what we got? Where did I do that at? Right here. So go ahead. I got you. All right, what's up?
No,
Hmm? Down?
yes.
I got you. Okay. So then this is 44.47267 less than mu, less than, then we got to add them. Let me see. So this is 46.14 plus, give me 1 second. No, well, yeah, they are. Yeah, yeah. All my answers are like that. So this is the 47.80733. Bam. That's my answer. Nope. I just added and subtracted. That's it. The mu. I don't know what mu is. I'm estimating what mu could be. That's what this whole lesson is about. Just sign when you get a chance, man.
All right.
So we good?
All right.
Y'all have all the information to do y'all homework now. I have just a little bit to talk about, then we can call it. Go ahead. The what? As soon as it downloads. Probably not tonight, probably tomorrow, because it takes a while to download.
See you next.
Yeah, let's see.
See you.
Yeah, I just updated everything on YouTube. Mhm.
Where's the tutor today?
Nah, but I got y'all. Don't worry. So real quick, last couple of things I'm gonna say, right? So the archaeologists can be 99% confident that the interval from 44.5, they rounded it up, to 47.8 is an interval that contains the population mean mu for the shoulder height of the species of miniature horse. All right. So just let me give y'all a nice little quick summary of everything, putting it all together, and then we could call it. All right, here we go. Nice little quick summary, right? So we have several formulas for confidence intervals for the population mean mu. How do we choose an appropriate one? We need to look at the sample size, the distribution of the original population, and whether or not the population standard deviation sigma is known. All right. So this is the summary for confidence intervals for the mean. Assume that you have a random sample of size n from an X distribution and that you have computed the sample mean, X bar, and a sample standard deviation S. A confidence interval for mu is X bar minus E less than mu less than X bar plus E, where E is the margin of error. How do you find E? It depends on how much you know about the X distribution. First situation, most common. Let's say we don't know what the population standard deviation is, right? Sigma. In this situation, you use the T distribution with the margin of error, which is the T critical times the sample standard deviation over the square root of n with the degrees of freedom of n minus 1. Although a T distribution can be used in many situations, we need to observe some guidelines. If n is less than 30, X should have a distribution that is mound shaped and approximately symmetric. It's even better if the X distribution is normal. If n is 30 or more, by the central limit theorem, it implies that these restrictions can be relaxed. All right, here's a second situation that could happen. All right, it almost never happens though, but I'm gonna tell y'all about it anyway. All right. Got you. Mhm. So here's a second situation, right? You actually know the population value of sigma. In addition, you know that X has a normal distribution. If you don't know that the X distribution is normal, then almost there, almost there, almost there. So then your sample size, n, must be 30 or larger, right? Then your sample size n must be 30 or larger. In this situation, use a standard normal z distribution with the margin of error e is equal to z critical, right? Times your population standard deviation sigma over the square root of n. So which distribution should you use for the x bar, right, for your sample mean? Examine the problem statement. That's step one. If you know what sigma is, then you use this this margin error formula, z critical sigma over the square root of n. If you don't know what sigma is, then you use this E formula. E is equal to T critical times the sample deviation over the square root of n with the degrees of freedom of n minus 1, right? Sigma is your population standard deviation, right? Then you use the other one, right? I'm circling that. You should read into that while I'm doing that. Mm-hmm. All right, that's it. This next part is just for Sarah. Yeah. I'll make a comment real quick. All right. Yeah. So to find confidence intervals for mu based on several samples, we need to know that the population distribution is approximately normal. What if this is not the case? The procedure called bootstrap, right, utilizes a computer program to generate an approximation for X-bar sampling distributions. Essentially, the bootstrap method treats the sample as if there were a population. Then, using repetition, it takes many samples, often thousands, from the original sample. This process is called resampling. The sample mean X bar is computed for each resample and a distribution of sample means is created. For example, a 95% confidence interval reflects the range for the middle 95% of the bootstrap X bar distribution, right? So if you read using technology at the end of the chapter, you will see the bootstrap method, blah, blah, blah. That's it. Have a good night. Have a good weekend, right? Yeah. I got y'all. I got y'all. Can I take this down? Awesome. Appreciate y'all. Of course, all the time.